Okay, today we're going to talk about alkanes, and alkanes are hydrocarbons having only carbon-carbon and carbon-hydrogen bonds, so there are only carbons and hydrogens in alkanes. And you can have them as linear structures or acyclic, or else ring structures, which of course are cyclic structures. An example of an acyclic alkane shown at the bottom of this slide, that's undecane, and notice the molecular formula of undecane is C11H24, and that means that the molecular formula you see there for the alkane, CnH2n plus 2, fits undecane. 11 times 2 plus 2 is 24, so that shows that this is an alkane. If this were an alkene, if it had a double bond in it, that formula would be different. So the CnH2n plus 2 formula allows you to know from the molecular formula standpoint whether you have an alkane or a different kind of molecule. We have in acyclic alkanes only linear or branched chains of carbons, and we call these saturated hydrocarbons because they're saturated with hydrogens. That is, they have the maximum number of hydrogen atoms per carbon. Unsaturated hydrocarbons, just for your information for now, are going to have, for instance, double bonds. So for now we deal with saturated hydrocarbons, which all alkanes are, and they have the maximum number of hydrogens per carbon atom. Let's, what did I do? I changed it. I kept getting this pop up. I should start over. Should I start over?
Just
keep going.
Okay.
Okay.
Have a pause and then start over.
Okay. All right, today we're going to talk about alkanes, and first acyclic alkanes. And as the name says, those are alkanes that don't have a ring structure. Alkanes in general are aliphatic hydrocarbons that only have carbon-carbon and carbon-hydrogen sigma bonds. And that means you're only going to see a carbon or hydrogen atom in an alkane. Acyclic alkanes have molecular formula CnH2n plus 2. And if you look at the example at the bottom of the page at undecane, the formula is C11H24. So there are 11 carbons, 24 hydrogens. And if you plug that into that simple formula, you'll see that it matches 2 times 11 plus 2 is 24 hydrogens. And that tells us that we have an acyclic alkane. Acyclic alkanes contain only linear and branched carbon chains, that is hydrocarbon chains, and they're also called saturated hydrocarbons, and that's got to do with them not having double bonds, having all sp3 hybridized carbons. In other words, they all have the maximum number of hydrogen atoms that each carbon can accommodate. Okay, so let's talk about cycloalkanes, and these are going to be ring structures, and these have a different general formula, just CnH2n, because they have 2 fewer hydrogen atoms due to the extra bonding. Okay, so cyclohexane, shown at the bottom, has the formula C6H12. Again, just fits that simple formula, and that's how one way you can distinguish an acyclic from a cyclic alkane is simply by molecular formula. Okay, so here's a very important and fundamental concept that's just going to be very general and very broad throughout your study of organic chemistry, and that's the concept of tetrahedral carbons. So what do we mean by that? Well, carbons have 4 atoms, 4 groups that can attach to them. They're sp3 hybridized, tetrahedral geometry, and all the bond angles are at 109.5 degrees. Why? Well, because if a molecule can, it'll keep things as far away in space as possible. So 4 hydrogens in methane stay as far away as they can from each other, and so the bond angles turn out to be 109.5 degrees. And you can see these examples at the bottom, and the 3D representations, which we're going to study in class, show exactly what these sort of look like in space. Now, notice the difference between, or actually the similarity between, the 3D representation and the ball and stick model. Okay, so we're going to be covering that in some detail. And one of the things you're going to have to really get out of the study of this chapter and the next chapter is how these 3D representations can be visualized, and how you can interconvert the geometries from a model back to what you see represented on paper. Okay, so let's go on. Okay. So let's take propane as an example, and propane as an acyclic alkane, 3 carbons. That means it's going to have 8 hydrogens, 3 times 2 plus 2, and notice that in the 3D drawing below, each atom has 2 bonds in the plane and 1 in front on the wedge. So remember the wedge projections, that is the dark solid lines, they are atoms, they represent bonds and atoms coming towards us, and the dashed lines are going away from us, towards your screen or away from your screen. The regular straight line drawings, the straight line or solid line that's not highlighted or shaded, that means that group or that bond is in the plane of the screen. Okay, so shaded dark line means the atom's coming towards us, dotted line is going back away from us, and the regular shading is in the plane of the page. Okay, so you can see that the way we would draw propane is represented in the middle. If you're just going to draw it, and you'd want to have this sort of zigzag chain in the plane of the page, HCC, CH, and draw the hydrogens that are on the carbon pointing up, draw one towards us and draw one back, and on the carbon that's zigzagging down, you draw a hydrogen down and towards us, and another one down and away from us. Why? Because each of those individual carbons, when drawn that way, represent a tetrahedral carbon. Okay, and you can show that in your ball and stick model if you take that and compare that to the ball and stick model of just methane. Okay, so there are different ways of drawing molecules, and if you're going to draw all the carbons and hydrogens in as shown here, you can actually curve this around or draw it straight across, which is more common. But what you have to realize is that there's free rotation about all these bonds, so both of these structures shown here are equivalent. And don't be confused if you see a structure drawn in a strange way, like on the right, for instance. It really is the exact same thing as the structure on the left. And so, yeah, the more common way is to draw things straight across, but just realize that if you just rotate the bond, change the bond, the way the bond is drawn up, down, or sideways, that in this case anyway, we're drawing the same compound. Now notice that these are Lewis structures. That means we're not drawing the wedges and dashes. Okay, so we're not taking into account some of the stereochemistry that we represent by things coming towards us or going away from us. But either way, these two structures you should recognize as equivalent. Okay, so there are cases where we have structures with the same molecular formula that aren't equivalent, and this is a really key concept of constitutional isomers or structural isomers. So this is the first time I think we're going to come across the concept of isomers. So again, this first example, the most general example, is when you have two compounds, same molecular formula, that are actually different structures, completely different, not just because of the way they're drawn, but because of the positions of their atoms. So take a look at butane on the bottom left there. That's a straight chain 4-carbon alkane. So 4 carbons means we're going to have 10 hydrogens. And isobutane, notice isobutane has also 4 carbons and it's got 10 hydrogens, but it's a different structure. The connectivity of the carbons, the connectivity of the atoms in general is different, yet it still has the molecular formula that of butane. That relationship is called constitutional isomer, okay, or structural isomer. Same molecular formula, but different bonding pattern. Okay, so this is a relatively simple concept. We can describe carbons as primary, secondary, tertiary, or quaternary. And just like these numbers and degree symbols say, primary carbon is a carbon bound to just one other carbon atom. Okay, so secondary carbon, guess what? Bound to 2 others. A tertiary carbon is bound to 3 other carbons, and a quaternary carbon is bound to 4 other atoms. So in a primary carbon, typically, if we're bound to 1 other carbon atom, we're typically, in an alkane, of course, going to be bound to 3 hydrogens. In a secondary carbon, in an alkane, we're going to be bound to 2 hydrogens. So let's take a look at the examples in the bottom. Primary carbon, 1 bond to carbon, 2 carbons. Secondary, the carbon in the center here is bound to 3 other carbons, it's tertiary. And over here, quaternary, as we have that carbon bound only to other carbons, and that fills up its valence with 4 bonds. So typically, one gets asked on an exam or quiz or whatnot to label the types of carbons on a molecular structure. And you see that done in the example on the lower right here of slide number 7. Primary carbon, you can see it's bound to 1 carbon. And that means if it's an alkane, the valence got to be filled with 3 hydrogens. Secondary carbon, you can see, is bound to 2 other carbons. The tertiary carbon in the center there is bound to 3, and the quaternary is bound to 4. So I hope that is simple enough. It's supposed to be. And guess what? We can do the same thing for hydrogens. And we classify hydrogens based on what kind of carbon that they are bound to. So take a look at the lower left examples there. A hydrogen that's bound to a primary carbon is called a primary hydrogen. A hydrogen bound to a secondary carbon is called a secondary hydrogen, and a hydrogen bound to a tertiary carbon is called a tertiary hydrogen. Is there such a thing as a quaternary hydrogen? No, right? Otherwise, it would be on this slide, first of all. But a quaternary hydrogen would have to be bound to a quaternary carbon, which means the carbon's bound to 4 other carbons, which means there's no room for a hydrogen to bind. So we do primary, secondary, tertiary for hydrogens, but primary through quaternary for carbons. Okay? And again, simple example, in order to classify the hydrogens, you simply look at the carbon that they're bound to and see if it's primary, secondary, tertiary. Okay, again, hopefully that's very, very straightforward, relatively trivial. And so now we're going to talk about naming alkanes, and this is kind of an interesting, fun topic. The suffix, so we have a suffix "ane" that's going to identify an alkane. So we've heard of chemicals like octane. Well, that means there are 8 carbons, right? Makes sense. Pentane, 5 carbons. Propane, 3 carbons, right? And so you can fill in the number of hydrogens just by using the rule, provided these are all straight chain alkanes. You can fill in the number of hydrogens. You know, ethane, for instance, is 2 carbons, and that means it's going to have 6 hydrogens, methane 1 and 4, etc., and so on. Now take a look at this number of constitutional isomers column, and let's look at entry number 20, icosane, and that's got 366,319 possible isomers. Now, I'm not going to ask you to draw all of those, but just keep in mind that the number of isomers can increase exponentially as you get bigger and bigger, more and more atoms that can actually bind in all these different ways and give you this same molecular formula. You should be able to draw off the top of your heads the constitutional isomers, for instance, of butane, pentane, and hexane. And what you do is the straight chain alkane is going to be the first one, and then you want to create branches, and the branches of the branched structures are going to give you your isomers of the straight chain parent compound. Okay, so we saw an example with butane and isobutane just a moment ago. Okay, how about cycloalkanes? Well, cycloalkanes again have the formula CnH2n, and they're arranged in a ring. And here are some ring structures you see on the bottom as ball and stick structures, and also as just line representations. And it's easy to name these. If you have 3 carbons in a ring, that's called cyclopropane. 4 carbons in a ring, cyclobutane. 5 in a ring, cyclopentane. And 6 in a ring, cyclohexane. Okay, again, hopefully this is relatively trivial. And here's the part that's going to require some sort of a systematic approach, and that is realizing that once we start getting to a little bit more complex structures with different branches, etc., and so on, different atoms, we've got to think about naming every organic molecule in 3 parts. The parent name, first of all, it consists of the number of carbons in the longest continuous chain. So let's say you have a molecule with 4 atoms with 4 carbons. If it has a branch, the longest chain is going to be 3 carbons. We'll show you plenty of examples. So the parent name there would be a propane, whereas you have 4 carbons, and that would normally, if the 4 carbon chain were just linear, that would just be butane. We'll come back to this. The suffix indicates what functional group is present, so the suffix is going to be ane for alkanes, ANE. So that's not going to change as long as we're dealing with alkanes. So we can always get the suffix right, and you want to look at the longest chain in the atom of carbons, and that's going to be we're going to write that right before we write the suffix. So again, if the longest chain is 3 carbons, the longest straight chain is 3 carbons, we're going to have a propane or propane derivatives. Okay, now the prefix tells us about everything else. The identity, location, and number of substituents that are attached to the parent alkane. Okay, so when you have other hydrocarbon substituents attached to a chain, we call those alkyl groups. And an alkyl group we draw by removing 1 hydrogen atom from an alkane. Why? Because we need a bond left over to bind to the carbon chain. Okay, so an alkyl group, you use the suffix YL instead of ane. So if you have a methyl group or a CH3 attached to a longer carbon chain, that's called a methyl group. If you have a 2 carbon alkane that's attached to a longer parent hydrocarbon chain, that's called an ethyl group. Okay, so let's go back to the example we promised and see how some of these work with 3 and 4 carbons, at least at first. So so these have more than 1 type of hydrogen. We've got in propane primary and secondary hydrogens, and you can if you remove one of those, if you remove a primary or a secondary hydrogen, we're left with different alkyl groups that can attach to a molecule. So we have an isopropyl group because it's going to attach in the middle, or a propyl group, straight chain, that's going to attach on one of the end terminal carbons. So again, realize if you start with propane and you want to create a propyl group, P-R-O-P-Y-L, that is, you want to attach 3 carbons, a 3-carbon alkane, onto a longer parent hydrocarbon chain. You can attach it at the end, remove one of these primary hydrogens, or attach in the center and remove the secondary hydrogen. If you move the middle one, you have an isopropyl group. If you move one of the 2 terminal ones, either one, you have a propyl group. Okay, and for butane, we can create butyl groups. A butyl group, if we attach at the primary carbon. If we attach at a secondary, one of the 2 secondary carbons, we now have a sec-butyl group, or a secondary butyl group. See, at least here, sec relates back to secondary. It actually directly relates to how we classify the carbon that is going to be attached. Of course, once you attach this carbon to another carbon, longer carbon chain, that carbon is going to become a tertiary carbon. Okay, but it starts out being this group alone that's going to attach it has a secondary carbon that's doing the attachments. Don't get confused. In this case, just looking at it this way, this is a secondary carbon because it's attached to 2 other carbons. When this is drawn attached to a longer chain hydrocarbon alkane, this is going to be a tertiary group. Okay, so look at another example, and this is an isomer of butane, isobutane, or 2-methylpropane. We see that there are 2 ways to attach it. Notice that these 3 methyl groups, they're actually equivalent, right? There's no difference chemically in any of these 3. But then we have this tertiary hydrogen. So if we attach at this central carbon, we're going to have what we call, it's a very common group, a tert-butyl group, tertiary butyl group, because it derives from the attachment of a tertiary carbon to a longer chain. The isobutyl group is going to attach at one of these other primary carbons. We call that an isobutyl group. So these names seem a little confusing probably at this point, but we use them so much that they become second nature. So let's try to put everything all together and do some nomenclature. And this is just a stepwise process. You take a look at your hydrocarbon. Now we've just drawn the carbons in for some clarity. Realize that the hydrogens are there. We're just using this as sort of a bare bones, literally, example. So the first thing we do is we find the longest continuous carbon chain. And so we count across 1, 2, 3, 4, 5, 6, 7, 8. And we know that this is going to be an octane, oct as the parent and ane as the suffix, 8-carbon alkane. Okay? Assuming that this is an alkane, and we are, because it says naming of alkanes. All right, now we could have counted this way and then up, and we would have used 7 carbons as our longest chain had we missed the fact that there is an 8-carbon chain across. Okay, and if you did that, you would incorrectly name this as a parent and suffix heptane, and that would be wrong. Doesn't matter if the chain is straight or bends, you just look for the longest chain, the one with the most, the chain that contains the greatest number of carbons. 8 this way, counting this way. We could have drawn it up this way, still 8 is the longest, 8 is the longest. All of these are the same, and realize that sometimes if you count this way, if you count up or across, don't think that it's always going to be the chain that's shown going lengthwise that's going to be the longest. Very often you can have a branch that it appears to be a branch, but just from the way things are drawn, but that actually can be the longest chain that there is. Okay, what if you have two ways to count the longest chain? One is this way straight across, and one is this way branch, and we have 7 atoms in the longest chain here and here. There's a tie. Okay, so there's a tie. What do we do in the case of a tie? We could go home and go to sleep. It's something I feel like doing sometimes, but no, there's actually a rule to take care of this, and you want to see how many substituents, or that is branches, there are off of the longest chain. So this one has two branches off of this long chain, and this one has only 1 branch off of this long chain. So who wins? Well, the longest chain that has the most substituents, again, 2 substituents versus 1. The one with the most substituents wins. So the rich get richer here. Okay, so we're going to name this compound using this chain. Okay, using this particular 7-carbon chain and not this 7-carbon chain. Does it matter? Yes, because remember in the prefix we're going to say where and etc. the substituents are. And clearly the substituents are going to show up as 2 different substituents here, whereas only 1. So it's going to matter in the nomenclature. So here's how we number these alkanes with substituents. So we could start from either end. We could have 1 from left to right, or we could have started carbon 1 from right to left. And again, could be a tie, but there's a rule here again. The first time you come to a substituent, when you count from 1 and higher, whoever gets to a substituent first wins. So you could see carbon 2 has a substituent here, but if we start here with carbon 1, we have to wait till carbon 3 to have a substituent. So we use this numbering system as the 1. Okay, that's going to be the correct numbering system. Is going to have the lowest numbered substituent. Okay, the one with this is going to have a substituent in carbon 2. This one has 3. So again, the lowest one is the lowest chain substituent is going to be the one on the left. All right. So how do we take a look at this? We're going to consider another possible tie, okay, and that is, what if you have two parent chains and they both have substituents on their second carbons? Okay, so we go then to the second substituent, and this one is 3, and this one, if we counted this way, would be 4. So how do you know, these actually are the same compounds, representing the same compounds. How do you know which way to start? Where do you number 1? If you get to 2 at the same, if 2 in both cases have substituents, you then go to see the second substituent that you come across, and the chain numbering system, where that's the lower number, that's going to be the one that you use. So the second substituent here is on carbon 3. The second substituent here is on carbon 4, so we use the lower number. Okay. So how do we actually name these and number these from either end? Well, we want to, if we have the same numbers from either end, okay, same numbers, you have a substituent here, so now we have a double tie. Okay, we have 3 and 5 here and here, 3 and 5. They both have substituents. So now we've got 2 ties. All right, so what we do is we go alphabetical. Okay, we're going to go alphabetical, and we're going to, therefore, E comes before M. We have an ethyl group, a 2-carbon substituent here, and a methyl group here in carbon 5. So ethyl is at 3. We've got the first letter of the alphabet, the lower letter of the alphabet at carbon 3 at the lower carbon number. So that's going to be the way we do this. If we numbered from right to left, we had come across a methyl at 3 and an ethyl at 5. M here is coming before E, which we know from the first grade, or sooner maybe, is not correct. Okay? All right, there are a lot of rules, but with a little bit of practice, this actually becomes trivial. Take my word for it. Just do your homework. Okay, so let's name our number. Okay, so we name the substituents as alkyl groups. Okay, remember what those are? That's when we need to form a bond to another hydrocarbon. Every carbon belongs to either the longest chain or to a substituent chain, not both, in alkanes. Okay, and that's all we're dealing with right now. So every carbon is either going to be part of the longest chain or a substituent. Right, so we've only got two possibilities in alkanes. Each substituent, if it's different from another substituent, it's going to get its own number, and it's going to be numbered based on how we count the carbons. And if two or more identical substituents are bound to the longest chain, we use prefixes. So if you have two methyl groups, we'll call it a dimethyl. Three methyl groups, that is three of the same substituents. Let's say three ethyl groups, we call it a triethyl. Tetra, etc., and so on. Okay, so this compound has three substituents that are bound to its longest chain. We have a methyl at carbon 2, ethyl at carbon 5, and another methyl at carbon 6. This is going to be a dimethyl. And what we're going to do is try to complete the name now. Just put it all together. All right, this is what we've been waiting for. Okay, so take a look at our carbon containing structure. It's an alkane, we're assuming, and we see our longest chain, 8 carbons. So we have an octane. And then we look at our substituents. We have a methyl at 2, we have an ethyl at 5, and we have a methyl at 6. So we have two methyls. That means we're going to have a dimethyl, 2,6-dimethyl. You see where the numbers come from? Carbon 2 and carbon 6. But since they're the same substituents, we're going to put it all together and call this a 2,6-dimethyl group and 5-ethyl. Okay, 5-ethyl. And so we put this all together as 5-ethyl, 2,6-dimethyl. Now, why did we put ethyl first? Especially since it's got a higher number than 2. That's because we're going to do, when we put everything together, it's going to go in alphabetical order. Okay, so we have 5-ethyl, 2,6-dimethyl octane. 5-ethyl, 2,6-dimethyl octane. E for ethyl, M for methyl. Don't count the D for dimethyl when you're alphabetizing. Just use the substituents. So we put this whole thing together. We have a 2,6-dimethyl array here and a 5-ethyl. So 5-ethyl, E before M, 2,6-dimethyl octane. And notice that we use dashes in between when we do the substituents, commas in between numbers for the same substituent. Okay, so dash after 5, dash after ethyl, 2,6, dash dimethyl, and then octane. Okay, and there's your full answer. And this comes with some practice. And again, you separate the numbers by commas when they're together and separate numbers from letters by hyphens. Pretty simple. And the name's a single word, no spaces after the hyphens or commas. Okay. 2,6-dimethyl ethyl, so we make that ethyl 2,6-dimethyl and put it all together again, just as shown before. Okay, how about cyclic systems? Well, prefix, it's going to be cyclo, all right, in all these cases of cycloalkanes. And then the parent is going to be how many carbons are in the ring, and the suffix is the functional group. In this case, it's going to be alkane, so the suffix is going to be ane. Okay, and so if we had a 5-carbon cycloalkane, it would be cyclopentane. Okay, and of course, if we have substituents, we'll take care of that in the prefix. Okay, find the parent cyclic alkane, and we have a cyclohexane, 6-carbon cyclic structure, and we have an ethyl substituent and a methyl substituent. Let's see how we're going to put all this together. So we name and number the substituents. This is a methyl cyclohexane. We don't have to use the number 1 because there's only one substituent. This is a tert-butyl cyclopentane. Notice that, go back and see, this is called a tertiary butyl substituent because it comes via the attachment of what was a tertiary carbon to a bigger parent carbon chain. Okay, and go back, we covered that a few slides ago. And when we have more than one substituent, as we saw in the previous slide, you begin numbering. You give the number 1 and start at number 1, where you get the second substituent as a lower number. So if we start here at methyl, and that's number 1, and go to the other methyl and count 1, 2, 3 clockwise, right? We have C1 and C3, and C3 is the second substituent. Here, if we count counterclockwise, 1, 2, 3, 4, 5, now we could label the second methyl group, second substituent as C5. That's wrong. We want to keep the lowest numbers. So the name of this would be 1,3-dimethyl cyclohexane. 1,5-dimethyl cyclohexane is wrong. Okay, so again, the lowest number wins. Okay. Now, when you have 2 different substituents, where do you start? You have an ethyl and a methyl. Well, just like before, we do it alphabetically. Number 1 is going to contain, is going to be where we label the ethyl group because E comes before M. So C1 ethyl, C3 methyl, and the correct name here would be 1-ethyl 3-methyl cyclohexane, and we keep the alphabetizing there. If we started at 1-methyl 3-ethyl and did it that way, that is wrong. Okay, so again, if we have a choice of 2 substituents, number 1 goes to the alphabetical order. Okay, now if the number of carbons in the ring is greater than or equal to the number of carbons in the longest chain, we name it as a parent cycloalkane. But what if there are more carbons in the chain than there are in the ring? Well, then we name it as an alkane. Okay, so on the left side, the example, we have a cyclohexane attached to 4 carbons. So the 6 carbons in the ring are going to make the parent structure here a cyclohexane, and we would simply name this as butyl cyclohexane. 1-butyl cyclohexane, we don't really need the 1 because it's only the 1 substituent. So butyl cyclohexane. Here in the other example, we have a hexane as the parent because the ring has fewer carbons, so we call this 1-cyclobutyl hexane. Now we've made the ring the substituent. Okay, so on the left, the ring is the parent chain, and on the right, the parent chain is the acyclic alkane substituent part. So this on the right is 1-cyclobutyl. Cyclobutyl is our substituent, cyclobutyl hexane. Okay. All right. So here are some more examples. Ethyl cyclobutane, we don't really need number Y. So why is cyclobutane the parent that gets the parent and suffix? That's because 4 carbons in the ring and only 2 on the outside. So ethyl's the substituent, and cyclobutane is the parent. We have cyclohexane here, and here we have, what do we have here? Well, we have a sec-butyl substituent that is a butyl group, 1, 2, 3, 4 carbons that derive from a secondary carbon. It's attached, this attachment from the ring to the butyl group was made to a secondary carbon on the butyl group. So we call this 1-sec-butyl 3-methyl cyclohexane. Why? Because butyl, B comes before M. Okay, so 1-sec-butyl 3-methyl cyclohexane, 1,2-dimethyl cyclohexane. Okay, not 1,6. Okay, we want to come to the second substituent as soon as we can. Okay, and here we have 3 ethyl groups attached to a cyclopentane, so this would be 1, 2, 4 triethyl, so the same group, triethyl cyclopentane. Notice 1, 2, 4 dash triethyl cyclopentane, and you could have numbered this maybe 1, 3, 5 triethyl, but that's wrong because 2 is smaller than 3. We came to our second substituent sooner, naming that way. Okay, I just want to show you now some really interesting polycyclic molecules. So we have cycloalkanes that have more than one ring that are fused together, and these have some interesting descriptive names because they don't follow the official system, which may have been invented after people imagined these. And so these names are a little more straightforward. There's cubane, it's a cube, and that's how we would draw it as a molecular structure, and there's the model. So cubane, someone actually synthesized this. And housane, I guess if you use your imagination, that's a little house. Okay, and here's churchane. Again, you need some imagination there. And basketane, again, use your imagination. I'm not going to test you on these, but cubane is a very famous compound. You should know that one. That's probably the easiest one. If you can draw a cube, you've drawn cubane. Okay, that's it for our introduction to alkanes.